Hello everyone, and welcome back to DRS Data Labs. In today's session, we are moving beyond just running a multiple regression. We are going to validate it. One of the most critical assumptions for reliable p-values and confidence intervals is the normality of the residuals. Let's jump into SPSS and see how to check this. First, let's set up our model. We go to Analyze, Regression, Linear, and we will move our dependent and independent variables into their respective boxes. So wage is our dependent variable, and IQ, knowledge of the world of work, educ, expert, and tenure are our independent variables. Now, before clicking OK, we need to request our diagnostic tools. Let's click on Plots. And in the Plots dialog, we move Z residuals, which are the standardized residuals, into the y-axis, and we move Z-pred, which are the standardized predicted values, into the x-axis. Now we must also check the histogram and the normal probability plot or PP plot. Okay, now we click continue and then we click save. To perform formal statistical tests later, we need the residuals as a new variable. So under saved values, we check the standardized residuals. We click continue and then we click OK to run the regression. So we have here our regression. Now let's look at our visuals. And we start by the histogram. We are looking for a symmetric bell-shaped curve. And we can see that although bell-shaped, our curve is not symmetric, since the right tail is larger than the left tail. So we don't have symmetry, which means that we might not have normality. Now look at the normal PP plot. Here we want the points to hug the diagonal line as closely as possible. Since we have large deviations or an S-shaped curve, we might figure that our residuals are not normally distributed. So this is an S-shaped curve which deviates a bit from the normality. Now let's look at the scatter plot of residuals against predicted values. We can see that we have the cloud of points here hovering around the zero line, but we have large deviations to the north of the curve, which would mean to the right of the mean, just like we had in our histogram. We have large outliers, although we don't have a particular funnel shape, which would indicate heteroscedasticity, but it means that most probably we will not have normality and our residuals are not normally distributed. So after we look at visuals, and since visuals can be subjective, we want to have a formal verdict. So we go to Analyze, Descriptive Statistics, Explore, and we will move our newly created variable standardized residuals into the dependent list. And we will click on Plots and check Normality Plots with Tests. We press Continue. and we press OK. And we must know how to interpret the Kolmogorov-Smirnov and Shapiro-Wilk tests. So, Shapiro-Wilk is best for small samples, samples smaller than 50, while Kolmogorov-Smirnov is more adequate for large samples. And if the significance value is larger than 0.5, we will fail to reject the null hypothesis, which would be great because our residuals would be normal. The null hypothesis of this test is the normality, but here we can see that we reject the null hypothesis. So we conclude formally that our residuals are not normally distributed. But we can rely on the safety net of the central limit theorem. What if our test fails? Well, before you panic, consider your sample size. This is where the central limit theorem, or CLT, comes to the rescue. In large samples, typically large than 30, but ideally much larger in complex models, the sampling distribution of the regression coefficients tends toward normality regardless of the distribution of the errors. In datasets with a large number of observations, the CLT often ensures that our statistical inferences like t-tests and f-tests remain robust and valid even if our residuals show some deviation from that perfect bell curve.